So I received some emails and the student asked me to show the equations. So I purposely designed this sheet for you guys so you can see the entire equations will be here on the slide. The first equation, it will be kinetic energy, 1/2 mc squared. And the second equation is the gravitational potential energy. And here you need to be careful. Gravitational potential energy, you need a zero potential energy point. Otherwise, it won't make any sense. You do need that. So this part is quite important. So in other words, you do need to choose zero potential energy points for the gravitational potential energy. The next equation is the spin potential energy, just 1/2 kx squared. And so there is no need for choose zero potential energy point because x equals 0, so you automatically you get a 0 here. So this is equation number 3. And now this part is what will happen today. Before this, the condition in order to have a mechanical energy conservation is the work done by non-conserved force equals 0. So you see, did you see I have a W and C here? Means work done by non-conserved force equals 0. So then the mechanical energy is going to be conserved. Initial final is going to be exactly the same. So again, we must choose which one is our initial, which one is our final. So this is very important. You're going to see me show you how this problem can be solved. You need to identify which one is the initial. And the second one, which one is your final. You must tell me where is your I and where is it. Otherwise, you won't be able to solve this problem. You have to identify which one is initial, which one is our final. So this is a recipe. So the entire mechanical energy, in principle, you're going to have 3 terms as a GPE, SP, and KE. So they have 3 terms, you're going to add them up. And that's called mechanical energy. So in our class. Now, some of these terms may not appear. For instance, if there's no spring, then there's no need for SP. If there's no spring, this term is just gone. I mean, there's nothing there. So that will be the case which we should be careful. If the system does not change y, which is elevation, in other words, the y direction is not there at all. It's always keep constant. So you will see I do not need to put the GPE there. Okay, so that's the case. And if there is no spring, you do not have spring potential energy. If there's no the y change, so we do not have a y like this. Okay. So that's essentially a review what we learned last time. Now, what happens if the work done by the non-conservative force not equal 0? When we talk about equal 0, that's conservation of the mechanical energy. But what happens is it's not the same. And this is our topic today. So we will use the next slide to show you how we do the calculation. So today's class consists, the first part is going to be a practice, which we continued last time. We didn't have a chance to finish the entire example, but I will show you this time a whole lot more detailed. And then we use this one, so that's first part, essentially wrap up everything we discussed about the chapter number 6. And then the remaining will be devoted to chapter number 7. So that's our offense here. Okay, so in case if you do not have time to write them down, don't worry. I already uploaded to my OneDrive, and you have everything you need. Sounds good? So I'm going to skip to next ones. So the next one, work done by non-conservative force, is essentially going to be the mechanical energy change. So essentially, you're going to use the final mechanical energy minus initial mechanical energy, and this is the connected with the work done by non-conservative force. These are still theoretical. You do not see the entire picture yet, so don't worry. So we will go over the example problem real detailed, and then we'll show you the steps on the board. So do not worry. Essentially, we have this equation called the delta ME equals WMC. So that's what you're going to use them. And did you guys write this down already? Can I get a thumb up if you already wrote it down? Still need time, take your time. If you don't, just give me thumb up, so I know you will. Okay, very good. Yeah, just write this down. And this equation will be repeatedly used, I think, in the next exam, will based on these equations as well. So all you can do is screenshot. That's fine too. Yes, cool, perfect. Okay, so I'm going to move on to the next. Great, thank you. Everybody's good. So I'll move on to the next. This example, we did not have time to cover them completely. And this time, I'm not going to show you all the detailed steps, what you need to do. Okay. Let's reread the problem again. Essentially, you have a mass is pressed against the spring. So the spring is compressed in that direction. So I press that particular spring to one particular extension of 0.1 meter. So let's press that. Then it says some distance from it, and along a frictionless surface. So in other words, this surface for the moment is frictionless, and then it says following. There's another spring with a different spring constant. It's called K2 behind it. So that's that. The box is not the case of the first spring. In other words, it can slide freely. In other words, if you release them, it's going to move over to that direction. When it hit on this particular second spring, it's going to compress them further. And then the question is the following: how far delta x2 is going to be? So in other words, how much the compression is going to be. Now, when I tell you how to solve this problem, this is uniform. There is no change whatsoever. You're going to see me show you two steps needed. First step, you're going to show which one is your initial condition. Second is which one is your final condition. It's a really important, also rather simple initial final. That was it. So let me show you the step. First, we need to choose which one is our initial condition. So we will press that, and that is our initial condition. Makes sense? That is our initial condition. In other words, this guy is pressed like that. And the final condition is going to be release this guy and pressed onto the spring. So, and these are two steps which is going to be utilized. So, then we're going to write them down, and these two initial and final mechanical energy will be exactly the same. So we're going to solve for this. So that's the first step. And the second step, and we're going to solve for delta x. So that's the key step. So we're going to follow this recipe and show you how we do it on board. All right. So this time I need notes to show you. So I'm going to put the camera over here. For those who just came in, you can enter the access code. Here is 2179. So here what I want to show you is how do we solve these problems and really systematically. And we're going to follow the recipe that I just showed you on board. Again, I'm going to step-by-step fashion. I don't like this pen. So this is my step number one. So step number one is initial condition. Our initial condition is the spring compressed. That's my initial condition. So in other words, the spring compressed. To be more precise, spring 1 is compressed. So spring 1 is compressed in this case. And the block is static. So that is my initial condition. I just press this the spring and statically like that. That's initial. And my final, could you guys leave some space here? Leave some space here so that save my board in this case. My final condition is the spring 2 is compressed. So spring 2 is compressed. Okay, so you just basically, but the block is also static. So the block itself is a static. From these, we will be able to write down the mechanical energy. So again, mechanical energy has three terms. One is the gravitational potential energy, one is the spring potential energy, one is the kinetic energy. So we can write all of them down. But this time you see the elevate the same level, so gravitational potential energy is not being used. Can I get a thumb up? Everybody understand? In other words, there will be no gravitational potential energy. Great, thank you so much. Awesome. So in other words, you won't see writing down spring potential and the gravitational potential energy. So I will have SP and plus the kinetic energy of the block. How large is the kinetic energy of the block? 0, of course, 0. Okay, that's static. And this is my initial mechanical energy. Okay, so the spring is compressed. Let me write this down. Do you guys still remember what is our SP1? SPE is? 1/2 K X. Great, good job. So essentially that's what you have. Now spring number 1, we just put 1 here. X1, just put 1 here, and then we just square this way. Make sense? So that's why the knowledge we just reviewed is used for us immediately. So that's what we do here. The final one is a similar, and I'm going to write a little higher. My camera won't be able to catch the bottom part. So the kinetic energy is still 0 because the block is static, so there's not a mode. Now this time spring 2 is compressed. So you're going to see me write a K2 X2 squared. In our problem, they use delta X2. In my class, it's simplified, just called X2. They are exactly the same. Make sense? Just that way. And then, so then when they are equal to each other, so that's step number 2. So then we have a mechanical energy conservation. Essentially, you can see this one equals that one. That's the equation you're going to find, or equation you're going to see them. So in other words, step number 2, MEI, and EF. So these two are exactly the same, and this is what we are doing here, solve for delta X. So we just write them down, just 1/2 K1X squared plus 1/2 K2X squared, like this. So that's all we need. And then we're going to solve for this immediately. 1/2 cancels out. My K1 equals 571. My X1 is 0.1 squared. My K2 is 223 X2 squared. Now folks, solve for this. Everybody, solve for this. And I will check around if you still have questions. Let's solve for this, all right? Take your time, solve it. When you're done, make sure you check with your neighbors. If you still have questions, I'll please let me know. It's pretty good. If you still have questions, just raise your hand. So we run it a little quicker. Maybe there's questions. Can you check it? How do you do it? Yeah, we got X squared, X2 squared.
Okay.
Yeah. Okay. Yeah, make sure do not forget about X squared, right? Folks, when you got the answer, check what your neighbors. Remember we're very happy to see whether we got the same result, all right?
You just gotta take square root. I got it.
Yeah. Make sure to check with each other, folks. Check with each other. Check with the. I wish I had a longer ruler. Hello. Check with each other.
Do all that and use word and final number.
So now I can use my 10 inch.
5.5. Just put 1 squared divided by 5.75 equals 233 times x squared. So then you divide Yeah, I took 233, which gave me this. And I took the
You
square
want
root.
the around? Oh, wrong. Yeah. You're asking, you are writing it down there. Yep. All right, that's good. Yeah, anyone can tell me the answer, give me the answer. How large you got?
Dr. John, I'm right here. I'm on the line right there.
Oh, okay. Oh, you should be a phone college. All right. Okay, thank you. So I will move your name over there. Anyone can tell me how large you got?
I got 0.157.
0.157
Yeah.
is a point. Anybody else got different numbers? How large you got?
I got 0.161.
0.161. Anybody have different answers from these two? Okay, let's check, see whether the answer is correct. Yeah, the correct answer should be this guy's here. There's some way there's something incorrectly. And so this number times that, could you do me a favor? This number times that, and then how large do you will get?
I got 5.75.
Okay, divide by 223.
Yeah, is 0.0247.
Okay, square root of that?
Is, yeah, 0.157 is what I'm doing.
What kind of calculator you're using? That's kind of interesting. Okay, hold on to this. I was a little surprised. I really want to know what is happening. Okay, let's do it together. You got 5.75 divided by 223.
Oh,
Did you get-
223. I have 233. Oops.
223. All right. Well, that's huge difference.
Yeah.
I'm so glad to point this out. Okay, folks, this is good, right? Is everybody good? Do you guys understand this? Can I get letter A up? Give me the letter A up if you understand this. Okay, it's fine, might be easier. Letter A. Okay, cool. Everyone's good. So now we understand this is the answer. Now, the next step, which I'm going to show you, see if you are able to figure this out independently now. This is the continuation. It asks how fast a meter per second will the box will be moving when it strikes the spring. And you work this out similar fashion, and you choose initial final conditions, and then write this down, and then solve for here. And this one you work out independently. All right. You need to choose which one's your initial, which one's your final position. All right. So I will give you 2 minutes to figure this out. And work out, discuss it with your neighbors, follow my guideline there. My first one, this is my initial, and this is my final. What about in your case? What is your initial? What is your final? 2 minutes. So you find out which one is your initial position, which one is your final. So that is all. Before you get on the second, what that means? Before you get on the second, what that means? What that means? So initial, final. If you have questions, raise your hand. So that way we will be able to answer your question. Okay. Do we have anyone figured out the velocity? Okay, all right. Stay on 30 seconds.
No.
This is the part 2.
But it's
Part B.
because you're starting at a point where it has. Then you let go. That's
Can you go back so we can get the map?
Oh, sure,
Yeah.
absolutely.
But you have to release it from the first one. That's the initial point.
Okay.
Yeah.
So this time we'll calculate the velocity. Anyone has some idea already? Okay, anyone has some idea already? Okay, you good? Good. Yeah, how do you do it?
We use the kinetic energy equation 1/2 times mv squared.
Exactly. You guys hear it? Essentially, that's all you need. Probably figured out that that's already. So this time, folks, this time, the initial condition, this part does not change because that's still initial condition. But the final condition is different. Final condition is because the spring is not compressed. So here's a final condition. The final condition here is the block still moving, but the spring too is not compressed. So therefore, the mechanical energy, whatever you see here, is going to become m2 1/2 mv squared. So this is what you're going to see there. Okay. So then you're going to have this term here equal to this term here, and then you have another equation you can solve for Vf. Does that make sense to all of you? So that's all you need to do. So that equation is going to equal this equation, and that's what you get. Essentially, you are going to see equals me1 equals 1/2 k1 x1 squared. And then you can solve for velocity. So that's how you do it. Does that make sense to you? So I'm not going to show you all the details because that can be straightforward. I want to reserve some time for the last part of the equation. So for those of you who are interested in the results, I can tell you the answer. Could you guys write this down so you can back home you can verify it. You should get 4.1742 meter per second. So you're going to get that. So then we have some time for our part C. So for our part C. Part C is a little bit harder. That's why I want to spend some extra time on that. Let's look at the part C. Could you guys write on the mass, please? Because I'm going to, and also the frictions. Could you write on the mass? Because the next slide is the mass. And I wish you have 2 boards. That would be much better. Since a 1 board is kind of a limitation on that. You guys write this down already, mass? Good? Can I get thumb up, everybody? Okay, cool. Wonderful. So now we're going to look at part C. This time, it's assuming the friction is present. All the stuff is between the ends of the spring and equilibrium lengths. And the coefficient of the kinetic friction is mu, and that's also given to us. And then the question is that, how far that x squared in meters will the second spring now compress? Before this, the mechanical energy is conserved, but now the mechanical energy is not conserved. You see, again, when we solve it, we choose initial and the final condition. So that's all we need. Initial and final, that's all we need. So in this case, my initial condition and the final condition are exactly the same. In other words, part C, same conditions as part A. So they're exact same condition. There's no difference. But this time, because we have our friction does work, so therefore it won't be the same equation which we're going to use. So same condition, that's step 1. Step 2, and let's see what we will need to do. So step number 2, what we will do is the following. So we're going to use this equation, WNC equals ME final minus ME initial. In other words, this is the equation which you're going to see me write down. So WNC equals ME2 final ME1, or maybe initial, forgive me, final and initial. And this is the equation which we are going to utilize it. So that's the one that we use. Remember, this is different because you have friction now. We're going to use this equation directly to do that. Now we know the mechanical energy, the final, which is this expression here. So this expression, 1kF2 x squared minus 1/2, sorry, my 2 is crazy, 2. 1/2 k1 x1 squared. And this is what we have here. So this is the equation which we will have essentially. And let me see whether this is the correct one. Yes, exactly. So this is the one which we have. Now, remember, we are looking for how large this one is, x2 is. We know everything about the first, second term. In order to find x2, so we need to find out W and C first. Otherwise, we won't be able to solve it. So therefore, this is the extra step I called 2.1. Find W and C here. So this is extra step added into it because that's a non-conservative work. Folks, I'm going to show the results over here. Can I erase this part? You guys good on this? I'm going to erase this part. Okay, very good. So I'm going to write this down. So we're going to find how large W and C is going to be. So this is work done by the friction. So work done by the friction just equals the friction. So that's F. Displacement, I believe they use the D. Do they use a D? Yes, they use a D0 like this. And then we need to multiply by cosine angle. Now you see displacement angle this way, the friction to the left. What's the angle between these two? 180. Great. So that will 180 degrees. And this 180 it just equals -1. So now we can plug this in, FD0. So we need to find the friction. This friction, you remember, friction, the kinetic friction just equals mu Kn, which is normal force. So we're going to plug this normal force back into that top equation, which is mu and K. The normal force, because elevated to ground, this normal force just equals gravity. So therefore, this will be plugged into the top ones here. So in other words, you're going to see me write it down, negative mu K mg d0. So now let's check whether we are able to calculate this now. Do we know the mass? Do we know the mass? Yes or no?
Yes.
Yes. Do we know the mu K?
Yes.
Do we know the d0? Yes or no? Yes, D0 is given. So therefore, we are able to calculate W and C. So then, this is done. Then we're going to find this guy's here. Sounds good? Sounds good? I'm sorry I had to run a little faster, but I think that's how you need it. So the final answer, you get x2. And I want to show you the answer. So then when you're back home, before you do the homework, you can write this answer down. So that's x2 equals this amount. You see, this number is smaller than 0.16 if there is no friction. That's why it is reasonable in our case. Does that make sense? Okay. So that's how we do the calculation. Now, when you guys do the homework, you follow exactly the recipe that you have. If you have a work done by non-conservative force, we use this particular equation. But if it's a conservation mechanical energy, we use the top ones. Just remember, initial final condition you must identify. Otherwise, you get totally lost which one you need to use. Okay? All my keys are already posted, but there's no explanation. So that's why I want you. This will be very important and just show you all the details. And I wish some of you send me an email. Hello, I tried this, but I don't know how to solve it. That would be even more helpful so I can go over that. And this is my last slide for this chapter. And this chapter, we talk about chapter 6. Now we move on to chapter 7. Again, chapter 7 notes already posted here. So this is chapter 7. In chapter 7, I have a bunch of these files. And whenever you see number 1, which means this will be the first class will be neutralized. You see here, I found the font size a little too small, but you will be able to see. So I'm going to start with this one. This is the chapter 7. So now start from today. These slides are created by Dr. Ball, and I steal some of those ones which I liked it. And how do you like this physically? You'll be very impressed. And so, this chapter is chapter 7. Folks, it's chapter 7 now for you. In the textbook is chapter 8. So that's all. We're going to talk about two things. One is called momentum. And one is a collision. So how this actually works, the momentum of collision, and they are sort of related in many ways. Some of these slides I created, and I like these slides, so fancy. And this one is called Newton's second law and momentum. We're going to start with Newton's second law first, which we know that already. So Newton's second law is F equals ma, and then you know A is delta V over delta T. So this is the one you know already. At least you're supposed to know it. Now the momentum part is defined as, did you see a mass here? Did you see the velocity here? It's just these two terms multiplied by each other. And that's called the momentum. So that's how the momentum relate to each other. That's N and V. Now momentum, different from the kinetic energy, momentum itself is a vector. In other words, you have to understand, momentum itself is a vector. So it has to tell me the directions. So this way you know that how this actually can be calculated. So that we started with the Newton's second law, but now this time we introduce the concept of momentum. To be more precise, that's the equation which you might talk about. You see, exact same equation, all I need to do is just move this V together with M. So that's what you get this one here. Could you guys write this equation down? This equation will be utilized at the end of this section, so on maybe Monday session. We'll be utilizing it because we have another goal on this part. And we'll show you each one of them. Delta T is the time gap between two instants like this. So this is the equation which we have. Now, the first thing that you're going to learn is called a conservation of the momentum. You know, if two cars collide, what happens to their total momentum? So this is called conservation of momentum. Similar to the conservation of mechanical energy, but the conditions are different. And I'm going to go over these concepts and then show you a whole lot more detail. That we have some practices as well. Momentum is defined as mv. The font size is a little too small. I just want to magnify it. It's not possible. You guys can see this. I thought those folks in the back could be able to. I don't know whether they're able to see it, but it's just T equals n times V. The conservation, what that means is that initial momentum and the final momentum equal to each other. That's called conservation. They conserve each other. It's the exact same amount. So if you have two objects, now if you have two objects, this P, did you see a P initial? You'll have two terms because of two objects. So let's have P1I, P2I. So we have two initials. So you essentially have two cars, initial momentum for the car 1, initial momentum for the car 2. That's what you're going to see. And similarly for the final terms, you notice that the initial final is so important. Here's initial, final. It's so important. Everywhere you're going to see this. Now, so if this is just one-dimensional, we can solve it in this way, which is just simply have two terms, add up, and there's no need for the vector form. So you see here on the top I have a vector arrow, even though it's a little smaller, but it is arrow. But down here there is no arrow whatsoever because it's one-dimensional. So this is the one-dimensional, I can remove the vector arrow, but so that's the purpose of the V1. And I gave you 1 second to write this equation down. This equation is quite important. Could you guys write this down, please? In other words, we have 4 terms, 2 initial terms, 2 final terms, and 1b1i and 2b2i equals and 1b1f and n2b2f. When you finish, could you give me 5 marks? So I can move on to the next slide. Everybody's good? Can I get one more student? Okay, good. Everyone's good time. And these equations are quite important. You know, in the formula sheet, when you prepare for the quizzes, you make sure you write this down. All right, looks good. 1, 2, 3 seconds. It's kind of, I don't like these slides sometimes because it takes time to write. All right, I'm going to move on to the next one. So now second is a constructor question. How do we know momentum is conserved, right? We say momentum conserved. Well, this is a rather straightforward. Momentum is conserved if there is no net external force acting upon the system. So for instance, if you have two cars colliding, of course you have friction on the tie, but if the friction on the tie is small, so you still conserve. You can still consider conserve. So two key words are important. Did you see external force? Did you see here? Did you see that system? So I will emphasize these two concepts in the next slides. So just write this down. Net, there's no net force, and there's no on the system. So that is the one which we're going to use. So what is a system? So system, for instance, if I have two cars, car A, car B collide. Now watch carefully. If we consider our system contains two cars, then the forces between them will be, it becomes internal force. You know, if you consider two cars as your system, then force, whatever the reaction between them, sorry, these are all internal forces. So the work, the moment is still conserved. So in other words, now we ignore the friction from the road, otherwise they will always have, but that force is small, it's really small. If the two cars colliding, mainly not the friction on the road will make a huge effect. However, if the same two cars colliding, if we consider one of the cars as our system, then the momentum will not be conserved because you have another car considered separate from them. So sometimes you need to determine whether these two are actually the same system or different system. If you consider the same system, yes, conserved. Not the same system, not. So that's the key idea. So, and this concept jumps a lot. But now what I want to show you is called elastic collision. I'm going to write this down on board. That's so important. So I want to spend time write this on board. So we're talking about elastic collision. Elastic collision. Because this word will look like a benign word, so this is called elastic collision. But something hidden. Why? You think about this, elastic collision is just a really, but this elastic collision, what that means is that the momentum is conserved because elastic. Also, the kinetic energy is conserved. It's also from elastic. And now these equations are really long, and I don't think you can write them down immediately. If I were you, when I write this down, I won't spell this out. If I were you, I would do it like this. The top line, what I do, P1I, P2I equals P1F plus P2F. I will write it this way, much faster, because I just use letter and a P itself. Instead of write A and B. The second line there, I simply change to KE. Every P change to KE. KE, KE, KE. So then you basically done. If you copy all these terms down, it takes a lot of time. So top with P, 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 K, 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 that's all you need. Each of these KE just equals 1/2 mv squared. There's nothing new. There's no new information if you write them out. That's exactly the same thing. So that was much faster. You're going to write them down. 1I plus 2I, 1F, 2F, like this. So that's the same thing. So that's why this way you can see, take picture, all right. This way you can see it's much faster than those equations over there. You know? So this is much faster than when we wrote over there. And this takes a lot of time to write. I even do not know how to type such beautiful equations. Dr. Boss being able to type, I don't know it. But this looks great. Okay, so that's the equation which we have. Now, you can solve for this, but it's going to be messy. In other words, basically what we're telling you, you don't want to use these equations in the future. That's what, because it's really messy. It's difficult. Now, the one thing which we're going to talk about, inelastic. Did you see the keyword inelastic? So inelastic, I'm going to write down over here. So I'm going to erase some of these ones. Do I erase it? Yes, I erase it. And I want to purposely write this in, because this is very, very important. I don't want to just skip this quickly. When you have inelastic, whenever you see a word inelastic collision, this means immediately mechanical energy is not conserved. When you see elastic, ME is conserved. So these are the key differences. You can ignore the rest of this information here, but these are the key words. We never see elastic, mechanical energy is not conserved. When you see elastic, mechanical energy is conserved. So these are the two major differences. The remaining detail is not that important, but this part is really, really important. So then the momentum has conditionally conserved. Did you see if two cars, our system, if you consider these two cars, like these ones, it will be our system, then momentum is conserved. And the bottom equation, you don't need to write them down. Exact same thing that your P1IP plus P2I equals P1F equals P. So they're exact same. Otherwise it takes time to write the same. Now, the kinetic energy is not conserved because this guy comes from the mechanical energy conservation. That's mechanical energy is not conserved, so therefore the kinetic energy cannot be conserved. That's due to the elastical collision. And we need also a number of lines in order to solve for this. But one thing we can do in this guy, could you guys write this down? This is called a complete elastic collision. And this one, I need to write this down on board. Could you guys write this down? So I'm going to erase this part. This is the one which is extremely important case. And Dr. Balch used the letter perfect elastic. In other words, I normally call it completely inelastic collision. So this is called completely inelastic collision. What is the key message here? Here's the key message. And I use a box to show you. The key message is that all objects have the common velocity. Please box this 3 times. Okay, just make fun of it. And in other words, if you have complete inelastic collision or perfect collision, a perfect inelastic, like what Dr. Boss said. So these two objects is stuck together, so therefore they have a common velocity. And this makes things a whole lot simpler to calculate. So these are the basic concepts, and usually in the beginning we will let you know now, and I think we will show you some kind of another things, explosion things. This is just example, and momentum conserved, and you can write this following way like this. And we will practice now on this, the concept. It's a little bit heavy, so I'm going to show you some practice problems. So this time we're going to practice. Folks, these are the practice problems which now I'm going to go rotating in this equation. So first, let's practice on some of these ones. And so if you have an inelastic collision, you see here the momentum is conserved. And the kinetic energy is also conserved, and that is what we call elastical collision. In elastic collision, then the mechanical energy is not conserved. So these are the equations typically we use. Could you guys take a picture or write this down? Because there's one homework problem will meet these equations. Either take a picture or write them down directly. It's a little bit messy there. And you see the subscript index is quite important. I want you to take a picture like that. Did you guys stand with this? Okay, take a picture of those words. If you do not take a picture, you can't still get my slides. You should be able to read them. So this is some kind of words. You ready? Can I move? Oh, you don't need time. Everybody give me sum up about can I move to the next slides? Okay, very good. So we move to the next slide. So now the momentum practice. So here's an example I want to show you. Two identical cars, mass m, moving toward each other with the same speed, which means the velocity directions are opposite. When they collide, they stick together. What do you mean stick together, folks? What do you mean stick together? They are inelastic or elastic? Is it complete or incomplete? Should be complete, 100% complete. Excellent, wonderful. All right. What is the total momentum before the collision? What's total momentum before collision? Total momentum before collision. They move in the opposite direction. Mass are the same. What about their momentum? So one momentum will be P, another will be negative P. Right? Make sense? Can that make sense? So therefore, you can add them up equals what? Zero, of course. Now, after the collision, how large the momentum is going to be? Initial 0, final must be 0. Make sense? So this will be 0, 0 like that. So that's all you need. Now, what about the kinetic energy? Before the collision, so the kinetic energy will be written on board. I'm going to show you now. Before the collision, the total kinetic energy will be Ke1I plus Ke2I. That's initial kinetic energy. And now we can apply an equation. Again, the equation already written over here like this. So there's no magic. So this is going to equal 1/2 mv squared plus another 1/2 mv squared like this. So that is the initial. You add them up, just equals mv squared. Now, what about after the collision? After the collision, how large the kinetic energy is going to be? 0, make sense? It must be 0 because there's 0 velocity. So after collision, it must be 0 velocity, 0 kinetic energy. So this is going to be 0. So this is the one which I want to show you here. And this is, okay, so this problem we will discuss on Monday. So folks, I wish everybody on Monday, please preview my slides. So there's some of this where we spend extra time so we can focus this problem a little more carefully. See you guys on Monday, and make sure you do not forget about the homework, all right? It's very important. And you work on homework, and we're going to end this now. Okay, first, our report, website. And so this is everything. If you need something, you're welcome around there.
I feel sorry. Yeah, we're trying to look at all those letters. Those letters are absorbed. That my brain. Yeah, I know what